while you watch to these motion of these targets, of these chunk in space, I will talk what I'm doing. I started many years ago in Graz and established a laser ranging station here. That means the station is able to use laser to range to satellites to measure its distance. We improved and upgraded the stations during the years. I will show you details of what we are achieving now. And since about 10 years ago, we started to track or to range also to space debris. You have to see it this way. Some of these satellites are cooperative targets, as we call them, and that means they have retroreflectors mounted somewhere, and these retroreflectors redirect some photons back to Graz. But 10 years ago, we started to track also uncooperative targets. Uncooperative targets are, well, all the junk which is up there, old rocket bodies, upper stages, tanks, whatever. And we were successful, and I will show you some of the results, what we are doing. In my talk, I will not talk about how to remove that, but we can talk about that in the discussion after the presentation, because there are some ideas and there are some methods what you can do. Okay. I think you have seen enough of these funny images. Okay. I'll try to find back where I am.
So are these little white dots each orbiting the Earth?
Yes, these are parts, or these are chunk. This is chunk which is going around, which is still in orbit. Just a few words about satellite laser ranging, because maybe some of you will not be familiar with that. Basically, we have several satellite laser ranging stations around the Earth. We are firing laser pulses to satellites, number of photons, not much energy, but very short pulses, about 3 millimeter in speed of light, 10 picoseconds. We are presently working in Graz with a 2 kilohertz laser, and the photons are reflected on the satellite. And in Graz, we are using a single photon detection system. That means we are able to detect single photons with a certain probability of 30 to 40% or so. And we measure the time of flight, nothing more. We do not record the pointing. We just measure the time of flight. But we do it as exactly as possible. And so we get the distance to the satellite with a few millimeter accuracy. This is done by more than 30 stations worldwide, and we are measuring more than 100 satellites. I think now it's 140 selected satellites with retroreflectors. The advantage of that is it's an absolute measurement. It's very accurate. In terms of statistics, it's in sub-millimeters, and you can do a lot of things using such a method. This is just a rough image. Where do we have these stations? You see on all continents, or most continents, we have it. Large collection within Europe, a lot of stations also in the United States and in China and Japan, and 2 stations in Australia distributed over the world. So just to give you an impression of the satellites, we have passive satellites. That means there are no active elements on these mostly balls of different sizes. Like the first, this one is one of the most important one, Lageos, which has a diameter of about 60 centimeter and is rather heavy. The intention is it's a common target for all stations, and it is heavy just so that it is influenced only or mostly by gravity. And there are a lot of smaller or other passive satellites, just to give you an example of these things. We are tracking also active satellites. These are satellites which have radars on board or cameras on board or things like that. And for some reason, they want to know as accurate as possible their orbit. For example, they are measuring with microwaves their distance to the ocean. Then measuring with a few centimeter accuracy, we are exactly, let's say, 1,000 kilometers above the ocean. Then we measure the orbit and tell them, okay, but your distance referred to the center of the Earth is, let's say, 8,000 kilometers or 7,000 kilometers. And then you know exactly, you can derive the altitude of the ocean surface referred to the Earth's center. And such things and such combinations allow us then to recalculate the rising of the water surfaces of the ocean, or the disappearing of glaciers in Antarctica or in Greenland. These are the active satellites. We are ranging also to GPS. Let's call GPS satellites. We call them GNSS satellites. We have the GPS of the United States. We have Galileo of the Europeans. We have GLONASS of the Russians, and this is an example of a Chinese GPS satellite. And what you see on the right edge here, this is a panel of retroreflectors. It means there is a certain amount of single retroreflectors mounted. You need more than one retroreflector to get at least now and then one photon reflected back to your station from such distances. Okay, so this is what we are doing, and this is now an image of our station, of our observatory. We are in Graz, in Austria. Graz is the second largest city of Austria. Austria is small, and the second largest city is even much smaller. We just have close to 300,000 inhabitants, just to give you an impression. You see the main building of the observatory. In this dome, we have our laser telescope, and there is an optical telescope. The advantage of the station is we are on a small hill, very close to the city. This is good for operational issues, but not so good for atmospheric seeing, and it's not in terms of seeing, not a very good point. But well, the advantage of operational things is worth something. This is a close-up of our laser dome. What you see here inside is, is our the receive telescope. It's a half-meter mirror. And just on the side of that, you see the small transmit telescope. So while this 10 centimeter transmit telescope, we fire to the satellite, and with the 50 centimeter telescope, we try to detect the returning photons. The whole system needs a very high accuracy in pointing, because you have a laser beam which up there has maybe a diameter of a few meters or a few tens of meters, depends on the distance, and you have to hit a satellite which is moving with 7 or 8 kilometers per hour. So that means you even have to use some type of point ahead, because the time, the light needs some milliseconds to come up there, and in these milliseconds, the satellite is moving significantly.
Excuse me, at that distance, how much at that distance, how much spread is there on a laser beam? I mean, we think of it as being very small, but isn't it many meters across by then?
Yes, it just depends on the distance. To calculate it, we can use 25 microradians for the divergence of the laser beam. That means in 1,000 kilometer distance, you have 25 meter diameter of your laser beam. Just to give you an idea.
Okay.
This is a close-up of our laser. I like to show this because we bought that in 2003. And it was the only company at that time able to produce such a laser we wanted to have, and it was an Austrian company. No other company worldwide could do it, but unfortunately, I think some United States company bought the Austrian company now, and okay, well, but the laser is still excellent.
How do you hit a target that's so far away that's relatively small?
Good question. The answer is we have to know where roughly the target is. That means we get what we call predictions. So we know the orbit with a certain accuracy, let's say plus minus 100 meters or so. Then we are able to find it. And then we have to search around a little bit, and then we see from this point we get echoes.
So there's a little trial and error within the pathway.
Yeah, we can do it manually. We can start some automatic search through the computer. We'll look around for it. Here we have some. From this point, we get something. And sometimes we can see the targets. I will show you later if it is dark on the ground, and but the satellite is still in sunlight. Then with CCDs, with sensitive CCDs, we can see it. So I have to switch back to the presentation. Okay. So you can see it.
Yes.
Okay. So I was talking about this. This is just for somebody familiar with electronics. We started 20 years ago developing our own PC cards with so-called FPGAs, which is necessary to do such things. A lot of hardware on big chips with millions of logic cells. One interesting thing you have to keep in mind, we have to measure the time of flight. This was done usually by using some timer or some counter. However, if you go with kilohertz laser ranging, you need event timers because a lot of shots are simultaneously in flight. Imagine we are starting firing to a satellite, and before we got an echo from the first shot, we have fired already a few hundred more shots. So a lot of traffic is going up and down between Graz and between the station and the satellite.
George, just on that point, how do you differentiate the shots? You know, the first shot misses, but the second shot hits it. So how do you know the second shot isn't the first shot, if you will?
Because, as I said, we have to know in advance roughly the orbit of the target. And if we know the orbit, we know the distance, plus minus, let's say 100 meters. And then we just plot everything which has to be within or has to return from this band, from this distance. So it's so we know this photon was coming from that first shot or from the second one.
Yep, good, thanks.
You have to keep in mind all that is based roughly on statistics only. Because of course photons don't have any numbers or any remarkable properties. All you see, you will see a few of our residuals, and then it will be much clearer than when I start to explain it. A short word about accuracy. This is our accuracy in orbit. That means you see this is in millimeters. We are in the millimeter range, and we always try to get the best out of our stations, and we are constantly improving that. How does it look like? For example, you see here such a track. You see the, let's first talk, this is a Russian satellite reflector. This was launched, I don't know, 15 years ago. Has on almost every edge some retroreflectors, single retroreflector cubes. And this is, just imagine it's free flying and it's stabilized in orbit by gravity only. But that's not stable, so it's tilted back and forth, is oscillating back and forth. And what you see here are echoes. The green dots are echoes from one of these retroreflectors. And because you have a lot of retroreflectors here, you see a lot of different lines. So you see it's easy to see this line of green dots, these are echoes. And in between, this is just noise. And the purpose of such things is they wanted to check if the theories about how these things will move or oscillate in space in a free-falling way, if these theories are correct. Okay, now what else can you do? Because that's also important for space debris. Assume we have a satellite like this AJISAI, a Japanese satellite. This satellite is rotating, slowly rotating, about 2.5 seconds now for one complete turn. The satellite has retro panels like these ones here, and in between the satellite has mirrors. While the retro panels are for laser ranging, and the mirrors are reflecting sun photons down in direction to the Earth, if the incidence angles are correct. What you see here also, if you observe one of these retroreflector panels, they are coming a little bit closer now. They are at the closest point, and they are going away a little bit because of the rotation. Now, if you look at such an image, well, it doesn't say anything, but this is a close-up screenshot of about 1 million echoes. However, if you zoom into this large amount of data and select a 10-second out of that, it looks like that. And then here you see already these oscillations because of some plates are coming closer, some plates are going away. Looks very simple, but this allows us to see, to track the attitude motion of such satellites. If you go even closer into that, you see now about 2 seconds. That's one complete rotation of the satellite. And you can see very accurate or determine very accurate the spin period. Now we apply some spectral analysis. You get all these frequencies out of that coming from different retro arrangements. And if you track that for over the years, you see the satellite. This satellite has been designed to keep its rotation as long as possible. And it was very successful. They didn't use, as far as possible, any metal to avoid internal current, to avoid break due to the Earth's magnetic field. And so it's still rotating, and now it has about 2.5 seconds for one rotation. So this is just a short explanation how we track, how we measure the spin parameters.
What does cause it to slow down?
There are a lot of relatively small other effects. The one are the electromagnetic currents. You can try to avoid that. The others are effects like, let's say, heat transportation from one side of the satellite to the other side. While if we chose one side for a short time to the sun, it gets some heat, and the heat is then distributed not regular during the other part of the rotation. And this is slowing down. Gravitational effects are slowing down, but these are all rather relatively small effects. The difference I showed you at the beginning, the passive satellites, which are just heavy and just full of metal. When they started, they also had some spin, but the spin was completely removed within a few years. This is in terms of, in space, it's called synchronization. The same thing what happened in a larger scale with the moon. The moon is now synchronized, showing us all the time the same side. And these ball satellites, after some time, also show us always the same side. The advantage of our method.
Yeah. You said of the previous satellite that they had reflectors that were not made of metal. What do they make them of then?
Sorry, I didn't get it.
Okay, you said that the reflectors on one of the satellites, the one you were measuring, that you showed the data on the period. You said that they've gotten away from metal on the reflectors. So what do they use for high efficiency reflectors?
First, you can use non-ferromagnetic materials. So you do not see such current, magnetically induced current. Second, you can use plastic. And the mirrors and reflectors are made of glass anyway, and they are not influencing the spin.
Oh, glass. Okay, thank you.
The remarkable thing on such things is you can measure that very, very accurate, the spin and the slowing down of the spin. This is just one example. Go into what we call a light curve. A light curve is what we do in Graz. We have implemented in our station also a method to measure sun photons, which are just reflected diffusely or via these mirrors, diffusely reflected and detected by our light curve instruments. That means we just collect, let's say, for 10 milliseconds, how many photons are coming from the sun. And you see here, this is one of these reflections from AJISAI mirrors, about 10 milliseconds. You will see many more of such diagrams like this one here. This is a GLONASS 41. GLONASS, you know, that's a Russian GPS system. And for some reason, these GLONASS satellites have a lifetime of only several years. After 4, 5, 6 years, they fail. They are removed a little bit out of their orbit and have to be replaced by new ones. once they are released and once they are, let's say, space debris, for some reasons they start to spin. That's due to solar radiation pressure, due to gravity. There are several forces acting on these satellites. And if we measure light curves of these, you see it very nice, very regular, that this satellite is spinning with about 9 seconds for one period. Now, this is a collection of more than 40 such old GLONASS satellites where we have measured their spin. All of them, of these are debris satellites or defunct satellites. I'm not going into details, but you see from a few seconds up to a few hundred seconds, they have all sort of different spin periods. Up to now, there was no systematic detected which orbit or which orbital plane or what is the reason for such different behavior. This is also for, coming out of a light curve. If you see such an image, you see clearly the period. If you fold all these various periods into one period, what is called the phase dispersion minimization, then you see very clear the response of such a box wing satellite. A box means you have a cube or a box, that's the main satellite, which the wings, we call the solar panels the wings. So if this one starts to rotate, you see one side of the box, you see the second side of the box, third side, and the fourth side of the box. So also a nice clear visibility how these spin can be detected. Okay, this is just another explanation of spin. I will just skip that. Now, if you have such a target like this old Long March rocket, Long March indicates that it's a Chinese one. It is mentioned here, what we tracked was just this upper stage, the last part of the rocket. We tracked it about 1 month before re-entry, and we tracked it both with laser and simultaneously taking the light curves. So the result looks like this. The green dots are coming from the laser. These are the residuals from the laser in a zoomed view. And the white line is a summary of the light curve. Now you can, looks a bit complicated, but it indicates a lot of things. For example, if you look, just imagine you have a long cylinder and is rotating in front of you. So you see on one point, the residuals are closer and the residuals here are a little bit more away and then closer again, and so on. This one allows us to indicate the C that this cylinder is not rotating around its geometrical center, but around its center of gravity. So you see one shorter side and one longer side once it is rotating like that. And you can find out a lot of other things out of these space debris observations. And this is what we were talking at the beginning when we just switched on the mics and the videos. The Chinese rocket, I think it was launched in January this year. It's coming down now. It's scheduled for it was scheduled for a controlled re-entry. And this will occur in a few days on the coming weekend, but it will be a completely, it looks like a completely uncontrolled event. we are pretty sure that it is uncontrolled because it is rotating. And it's a huge thing, 30 meters times 5 meters, and weighs more than 20 tons. So that's much too large to burn up in atmosphere, so it will reach the ground and it will crash somewhere, hopefully in the ocean, not damaging anything.
George, the re-entry on that will clearly be visible, correct?
What do you mean with visible? You mean optically visible?
Yes.
Yes, definitely. If it is somewhere near people observing it, they will try to track it maybe during the re-entry with radar stations, but it's very difficult. Definitely it will start to burn up, but it's too big, too heavy to burn up completely, and a huge amount will remain, and it will crash into water or on the ground.
Is there any science to be learned by sending up a plane or something as the re-entry path is more defined, to track it and learn things from it?
The first thing is to prevent any problems. Also, it's almost impossible because it's you don't know exactly when and where it will come down. As I explained, they say they have a roughly 10% margin of their estimations, and if you have you can state it will come down in 10 hours. This is plus minus 1 hour. And in 1 hour, it goes almost 2/3 of the whole orbit. So no way to say that. And what we try to learn out of that is how long can we track it? Can we issue a warning, I don't know, 10 minutes before, and you say it will crash somewhere in China or so, but not really. You cannot do much.
Understood.
Question: if it suppose it does come down and it does land on land, obviously something that large a mass is going to cause some damage, possibly a crater. Any idea how big something like that might be? In other words, if it's coming towards me, how far do I have to run?
It's not a matter of how far, it's a matter of how fast.
How fast can you run?
Yeah, that's the main problem.
We'll find out.
Well, the only thing is people are just using statistics here and say, okay, 2/3 of the surface of the Earth is water. So you have a 66% chance it will come down into water.
But it has a band, does it not? I mean, there is an orbit, so we know that it's going to come down in some band around the Earth.
Yes. Yes, you are safe if you above or below, what was the limit? 50 degrees north or south of the equator. So, because the inclination is, I forgot the current, but you will be safe in Sweden or in Canada, maybe.
You can contact me after this. I have a weekend charter going to Antarctica, so we're fine.
Okay. The interesting thing is because of these eccentric orbit, it has started also due to gravitational forces. It has started to spin, to rotate, and it rotates rather fast already. So it's even more uncertainty if you want to predict the final re-entry also, because you don't know which side it is showing to the main, the atmospheric rest in these altitudes. Okay, this is what I want to show you is if you have something in orbit, it will remain for some time in the orbit. And that means if it is in an altitude of 1,000 kilometers, it will take something between 1,000 and 10,000 years to come down. If you have an orbit in a lower orbit, like we're talking about like Envisat in 700 kilometers, it will, the estimation is 170 years to come down. If you look at the small CubeSats, usually done by universities, they are always below 600 kilometers. And from this altitude, they are coming down within a few years, usually. And this is an international, well, rule. It's not a law, but it's a rule. It should be away from the orbit. It should come down within the next 25 years. Okay, this is just some piece of hardware. This is our telescope, and we have mounted our space debris laser here, which can range in both wavelengths, in the original infrared or in the converted green wavelength. This is just something special. And this is what such a space debris measurement looks like. That means what you see here are the residuals. The scale here is in meters. It's coming here. It was detected. And you see, without any doubt, these are the green fat dots are the echoes, the returning photons from the satellites. So this is just to give you this example. In terms of space debris ranging, this is an old image, but it hasn't changed much during the last years. While with cooperative targets, we can go up to the geostationary orbit, 36,000 kilometers, because they have retros, but space debris usually has no retros. So 2,000, 2,500, maybe sometimes up to 3,000 kilometers, we can get echoes. Just you have to keep in mind, there are no reflectors, just diffuse reflection on some rocket body has to bring back some echoes, some photons to Graz. Another problem is, while for cooperative targets, the orbits are well known because 30 or 40 stations worldwide are tracking them. This is not the case for the space debris targets. The space debris targets, the best thing we can do is to track them in the terminator period. A terminator period is the time of day when it is dark on the ground, but the target is still in the sunshine. And thus we can see it, and then it's relatively easy. You see the target, and then you point your laser exactly to this target, and then you will get the echoes. What we have done now in the last years to overcome these limitations, because this is just 2 or 3 hours after sunset or before sunrise, we have started to develop a method to do these observations or these measurements in full daylight. Because during daylight, the targets above you are always in the sunshine. So all you have to do is you have to rebuild your telescope that you can see something like stars in full daylight, in bright daylight. And we succeeded of that. And what you see here, the gray image, we have made an artificial red ring about this target. This is a rocket body photographed or seen in bright daylight, so we can see that. And as soon as we can see that, we can point with a laser to the target, and we can track it, and we can measure it. So this is just another thing how you see the echoes here. That's very difficult, and up to now, no other stations has achieved that, and we hope to make these type of measurements as a routine measurement in the near future. Another way how we measure debris targets, suppose you have, we call it multistatic experiment. you see Graz. We are firing to a debris satellite. This is the active stations. On the satellite, photons are reflected diffusely and distributed over Middle Europe. So any other stations like in Wetzel or Zimmerwald in Switzerland or the British ones, if they know exactly when we fired, then they can calculate how long roughly will it need for the photons going up and being reflected here. And then they can open their detector, and then they can also passively measure the time of flight of these photons. This has a rather severe effect because that means with one shot you can have several measurements distributed over some area, and that allows you a much better orbit predictions with only one or two passes, one or two measurements. This was our multistatic experiment. This is an example. These are the track of photons. These are Graz photons, I mean the laser fired from Graz, and the photons detected in Wetzel in Germany. The only difficulty was how to organize such measurements so that the people know exactly down to less than 1 microsecond when we fired in Graz. And that was done simply by predetermining, pre-stating that we will fire on this and that epoch our laser. We just have to keep the schedule for the laser pulses. This was something different, quantum key distribution. I will not go into this one. This may be some interesting thing. We managed to get, let's say, the Holy Galileo spare panel from AJISAI. They were very hesitating to give away this one. It is a spare part, and what we did is we made some measurements. You see, this is a large panel, and the retros are organized in rows. And if you tilt the whole panel a little bit, then you will get echoes mainly from here, then from this row, and from this row, and from this row. You see here clearly this pattern in the distribution in this histogram. And this again allows you to determine the orientation of the Galileo satellites completely independently and completely without their internal stuff. And this allows to determine this attitude. Okay, and I will skip also this. We made some tests here. What can we expect in future? There's one thing going on. We want to establish a worldwide network of laser stations which are able to track these space debris targets. This is to overcome the weather problems, to account for different path geometries, and. This will not solve the space debris problem, but for selected targets, we then would be able to determine very quick, accurate orbits. Why is that necessary? Because we have now more than 40,000 large targets in orbit. And because of this large number, organizations like AJISAI get almost 1,000 warnings per day that some of these 40,000 targets will cross each other closer than some limit. So there might be a danger. So how can you handle that?
What is the definition of a large target?
Large target, these ones which are, well, the number I said with 40,000, this is, let's say, 1 meter, 1 square meter, or 1 cubic meter, or more. That means it's really a relatively big thing. Okay, this is maybe not so interesting for you. We have started 20 years ago with 2 kilohertz, and we are now testing megahertz laser ranging. With one of the goals, not only to improve the measurements to the cooperative targets, but this one might also be able to range to space debris with much better success. Well, autonomous stations are going on and things like that, but that's not so important. So this was the main presentation I wanted to show you. Basically, I want to show you let's see, no, it's not. Anyway, I would like now to start the discussion and stop the screen, common screen using. So if you have now questions, or maybe you are interested what people are going to do with the space debris problem in future.
Georg, thank you. That was really amazing. It's much more complex than I ever thought it was.
Georg, I mean, I would have thought that various military organizations would be duplicating what you are doing. Is that happening? I mean, is like the U.S. Air Force in this business, or the Russian Air Force?
That's different. For example, in China, everything what has to do with space, it's a military thing anyway. There's no civil use in China. Military people are not so involved in these problems. Well, if I'm sarcastic, I would say up to now 4 military nations have done the following. They have launched a killer satellite and destroyed, just by crash into it, one of their own satellites. The first one were the United States, next one were the Russians. I think China was successful, and the last one was 2 years ago, the Indian. They launched a satellite, they crashed into their old weather satellite, and instead of 2 space debris objects, now they have 10,000 more.
I have a question.
Yeah.
Who owns the definitive catalog of near space objects, and how big is that catalog?
There are several such catalogs. One is, for example, you can get it from the internet. If you look for two-line elements, or TLE, you will get several addresses of organizations keeping these elements. The system works like this. There are several radar stations around the world operated by United States, China, Russia, and with radar, they are trying to observe what is flying around there in the orbit. And huge computers, when they detect something, try to identify the object and update these two-line element predictions every day, every hour, whenever there's something to do.
Do you know how many objects are in the catalogs?
In the one we are using, there are, the actual number is 48,000 something, but maybe 5,000 or 10,000 of them already were, what do you call it, were decaying, already have re-entered.
Thank you.
Georg, in the very beginning of the presentation, you showed an interesting animation. And I assume those were all the known pieces of space junk that are out there, and satellites that are going around the Earth, and all that stuff. Some of them are really far away, some of them were closer. Is there any way you could do a little narrative in terms of the kinds of things that are in different bands around the Earth? Because some of them seem like they're really, really far away compared to the Earth. And clearly there was clusters closer to the Earth.
Yes. There are, okay, if you check which objects are in which distance from Earth, there are the very low orbits, usually where the ISS is in 400 kilometers or so. Then there's a band, let's say from 700 kilometers to 1200 kilometers, which is extremely populated because all of these Earth observations, Earth measuring satellites are orbiting there. Then it's a little bit less populated, going up to, let's say, the GNSS orbits in 20,000, 23,000 kilometers. And then there, of course, is a huge population in the geostationary orbit, 36,000 kilometers. But in this orbit is, because it is limited, it is well regulated. That means there are contracts, there are laws. You cannot put just your satellite up there. That has to be coordinated. And after the lifetime in this orbit, you have to move your satellite away from this orbit. And it sounds strange, but they are lifting it up with the remaining fuel they have a few hundred kilometers higher in the so-called graveyard orbit. And nobody knows how to bring down these things from there, but they just hoping in, I don't know, in many, many years, there will be some method to remove all that.
I have a question.
Yeah.
What is the danger in low
Who's talking?
Can you get closer to your microphone, please? We can't hear you.
In low Earth orbit to new missions? Can you calculate that in any way?
Sorry, can you?
Howard, it's hard to hear what you're saying. Can you try closer, please?
Okay, can you hear me now?
Yes, much better.
Yeah. Okay, I'm actually, my nose is practically touching the screen, but it'll work. In low Earth, if you launch something into low Earth orbit, what is the danger then to your mission of all this space junk?
The danger is that one of these pieces will crash into your satellite or whatever. This is the danger.
Has it been reported?
Sorry?
Has there actually been impacts?
Yes, of course. There are always, because you have millions of very small parts also going around there, which cannot be tracked by radar, or not very good. And if you imagine the limit is of the size of these particles, which then become dangerous, is about 1 centimeter. If you have a bullet of 1 centimeter approaching you with 8 kilometers per second, then it goes through all these steel sheets. It will destroy your satellite. There have been records and measurements of such events, and there have been already several accidents where an uncontrolled upper stage was crashing into a functional iridium satellite. And again, creating out of 2 pieces, you create several thousand of pieces. And if you are going to launch something, one of your first duties is to calculate all these 40,000 orbits and to see if something is in your way while you go up there. And so you have to schedule your launch accordingly, or to select your way up. And it's already in this way. And in addition, this is because the entrance into space now is increasing. And the amount of launches per time unit is increasing and increasing. The space debris is not going to become less; it's increasing also. Just imagine companies like SpaceX are depositing now more than 10,000 of small satellites in a certain orbit. And it's clear that some of them will even crash into each other because they are not so much controlled. They cannot, they cannot really deviate. They have only a small amount of fuel. What we are all afraid of is that we are running into what we call the Kessler syndrome. That's if one or a few crashes appear, they have a multiplication effect because each piece out of that can again crash into some other satellites, and that will close up our entry into space for some time.
So essentially a space-based chain reaction.
Yeah, a chain reaction, definitely.
May I ask a question?
Yeah.
I wonder if the military or even the scientists have I'm thinking about a laser aimed at the satellites and destroying them. Is that a possibility?
Okay. There are a few possibilities. The first thing which has been studied now is what is called photon momentum transfer. Basically, if you have a very strong laser and you point with your laser to some target up there, there is a physical effect which is called photon momentum transfer. Basically, you push slightly, you can push the target with the photons slightly. However, this is very, very much limited because the transferred momentum is very, very small. That means it will have an effect if you have a target with a very large area and a very small mass. Like if you have a plastic cover of a telescope circling around there, then you might be able to change its orbit a little bit. So this is the first thing. People are now looking into that. The next thing is if you manage to have such a strong laser that you reach a certain energy density level at the target, that means you need about 1 joule on 1 square centimeter for the technical people. Then what happens on the surface is what they call cold ablation. That means the surface or some molecules of the surface are evaporated due to the high density. If these molecules are evaporated, there's a reaction because they can only fly away in one direction, and that will have a braking effect on the orbit of the large target. And now if you do that with a kilohertz laser, then the target gets 1,000 such tiny impulses, and that will slow down it. And slowing down means it will come down, and it finally will burn up in the atmosphere. Theoretically,
there's a program that the U.S. government is funding to take down drones, but that's at a distance of just a couple of miles. And they're using 10 to 20 megawatt lasers to shoot at a drone,
yes,
pick it up via radar, lock onto it, and then there'll be enough energy. But the concern there is that once it gets too far away, which is why I asked the earlier question, that the laser spread is such that you don't put enough energy per square, whatever, centimeter.
Yeah. That's exactly the problem. Theoretically, if you assume you can do that, then it would be, the method would be good enough that within a few years of continuous operation of several such stations worldwide, you can clean up the whole orbit, the whole space around Earth. This is one theoretical thing. But to achieve this energy density up there in some 1,000 or more kilometers, what would you need? You would need megawatt lasers. You need a telescope of, well, you can calculate that. It should have 25-meter mirror, roughly, to achieve the very small diversions. This mirror has to use adaptive optics to overcome problems of the atmosphere, and. Just in short, and what's an additional, such a thing, it might become possible in some years, but it's a very, very huge investment, and it's a dangerous thing. It is a weapon. You can maybe the militaries are interested to fire at I don't know, at aircrafts or so, but I do not see a way that something like that will be effective in the next years or so.
Georg, it seems like you're talking mostly about land-based solutions to solve these things. Are there any space-based solutions? You know, like a vacuum cleaner in space, if we alluded to earlier, or a big net or something like that to just grab this stuff and bring it down.
There are several projects that are going on called Clean Space and things like that. Okay, what will be done? There will be a few launches in the next years where they send up some satellites and some apparatus to catch one of these large targets like the Envisat or any other. And then these two together will slow down and eventually burn up in atmosphere. But you see the main problem, such a launch costs several $1 million. They are talking about 60 million, 100 million. And then you are removing one piece out of 40,000. So it's not really a vacuum cleaner at the moment.
Run me down, can you?
Yes.
I'll just try and talk somewhere.
I can run you down. This is just about finished.
Dan, can you mute, please?
Sorry.
Thanks. Sorry to call you out.
So these are the problems. I don't know what will be the real next steps. At the moment, as I said, like AJISAI has developed some programs which do the calculations for these 40,000 pieces, and they will check in the next few days or up to 5 days or so if there is a close encounter of two of these targets. And if that is closer than, I don't know, a few kilometers or so, then they will get a warning. The problem is the computer issues now about 1,000 such warnings per day. And so that is, of course, not anymore possible to handle it manually. So they are developing now some artificial intelligence programs to select out of that. What we are doing is if we get an information that, I don't know, in 3 days, two of these objects are forecasted to come very close to each other, let's say the computers out of the radar can tell you that they will have a distance of 400 meters, but plus minus 800 meters because it's not possible to make it more accurate. Then they start now to ask stations like our Graz station, trying to track that. And then we can say, okay, it will be not 400 meters, but 500 meters plus minus 100 meters. So that's then a clear way to make a decision. If one of the targets is still under control, then they can make a collision avoidance maneuver. But collision avoidance maneuver are costly because you need fuel, which is limited, and that costs you lifetime.
Can I ask a question?
Yeah.
Well, one of the basic principles of science is that as soon as mankind develops a technology, somebody turns it into a weapon. And the US military can turn off the local GPS. They can encrypt it so that only they can use it, so that the enemy can't use it, because it's important to know where your forces are and where the enemy forces are not, or where the enemy forces are. So it would seem almost not believable that the military wouldn't be figuring out how to disable somebody else's GPS system.
That might be possible, but I'm not a specialist in GPS. But I guess
about the satellites, just disabling the satellites.
Yes, but you have 28 satellites of the Galileo system. You have I don't know how many Chinese satellites. You have more than 30 GLONASS satellites. So they have a lot of work to do to disable all those, and they are also prepared to keep their satellites safe. So, well, but this is a military stuff.
Well, it may be difficult, but there's a line in the play, The Celestine. It's a Spanish play, and it translates: "There is no talk about the U.S. military. There is no mountain so high that an ass laden with gold cannot climb it."
Yeah,
but Jerry, the people who could mount such an attack are also vulnerable because they have their own GPS-like system.
Right, and they're afraid the enemy will get ahead of them.
Well, or that there will be a retaliation.
It's just like an arms race, except it's a different technology.
True.
My atomic bomb is bigger than your atomic bomb.
Yeah, okay. That's a good saying. No, but I have one remark to that. We were talking about public catalogs of space debris objects. Now, in this catalog, obviously there is at least no active military satellite, because they do not make their military satellites public stuff, but they are still there. What we have done now, which I did not show in my presentation, is we have found a method even to track their secret satellites. It's called stare and chase. That means we are just staring with our telescope into the night sky. And if we see an unknown satellite passing by, which is in the sun, so we can see it, immediately we can calculate the orbit out. Using the stars, we make blade solving and such things, so we can determine the orbit within 1 minute. And then we start our laser, the debris laser, and fire on that. And then we can have even a more accurate orbit of a satellite which is military, completely secret and unknown.
So do you have a catalog of these?
No, we do not have that, but there in somewhere in Europe, I forgot the country, exists a catalog. People are hunting for military unknown satellites.
Well, the bottom line there is, you know, it's an unknown satellite, but you don't know the owner, and you don't.
No, of course not.
And you don't know anything about it. Just know. I mean, it's just a sophisticated piece of junk that happens to be doing something important for somebody.
As I just said, as soon as we develop a technology, somebody will turn it into a weapon. There you go.
Yeah, exactly. What can be done is we tested this method. Of course, we tested it to basically known objects, because we don't want to hit with our space debris laser any of the sensitive satellites. We don't want to blind the satellite with our strong laser, which is almost impossible anyway, but we don't take any risk. But I'm sure military people are prepared to do something like that. Because if you have optics in space with some telescope and sensitive CCDs or devices behind, then you can blind it. On the other hand, we are preparing an experiment where we have to track ISS with our laser. It's not so difficult to track the ISS with the laser, but the most difficult thing is to get the allowance to do that, because they are afraid of, you are faced with arguments like, well, the calculation shows it is completely eye safe up there because it's 400 kilometers away. But what if somebody has a half-meter telescope and is looking with that from ISS down to Earth? Then it's not eye safe anymore. No, but there is no such telescope. Well, but you cannot be excluded. You're facing such arguments anyway.
Georg, where do you go from here? What are the things that are on the horizon that are exciting to you?
Sorry.
What did the next steps for you and your research and the kinds of work that you do? Where do you go from here in terms of what you guys do in terms of investigations?
Okay. One of the big projects we are just implementing now is switching or implementing a megahertz laser ranging system. That means you are not, look, around the world, 50% of the stations are using 10 hertz systems. This gives you a limited amount of measurements per time unit. We started 20 years ago with a 2 kilohertz. Now about 50% of the stations are using kilohertz systems. And we are trying to switch now to megahertz. This gives you, of course, a huge increase of the number of measurements per time, but also allows you, for example, to identify each single retroreflector if you have several retroreflectors as a pyramid or on a panel, and things like that. And it would allow for the first time, theoretically, we have not tested yet, to use the megahertz high accuracy laser, because it still has only 10 picosecond pulse length, to use it also for space debris. That means with one laser you can have everything what a laser station can have: high accuracy measurements and space debris measurement capability. So this is one of the things we are following now.
Interesting. Good. Go ahead, Ken.
Is there potential to modulate the laser pulse, with the newer technologies, so that way you can identify individual pulses amongst the set?
I'm not sure if I did understand your question. What we are doing, however, what we did already is with a 2 kilohertz laser, you can do what we call pulse position modulation. That means you are not firing the laser in exactly every half millisecond one shot, but slightly variation of the pulse position within this net, within these frames. And with that, you can transfer information up to the satellite. We are starting now that the ESA satellite called is OPSSat, OPSSat, a small satellite which has a detector and a retroreflector on it. And we intend to transfer with 2 kilobit per second information up there. And basically, basically that's also 2 kilobit is 16 kilobyte per second, and that's also already enough to make a telephone call up to the satellite if there is somebody.
Is there
can
potential?
Can you use polarization of the radiation in any effective way?
Yes and no. There's no direct use of that. There have been some experiments using the polarization to identify the material of the it was diffusely reflected. That sometimes is possible, but not very effective. What we did is, and now that goes deep into optics, if you have a panel, like you have seen on Galileo satellites or on the Chinese satellites, you can, we have installed something where we can rotate the polarization plane as we like it. And using this intended turning of the polarization angle has some optical effects, some physical effects, and we could demonstrate that the Chinese panels were close to perfectly orientated. This goes to the clocking, what we call the clocking of these 80 reflectors, retroreflectors. However, the Russians some of them were very bad. If you rotate the polarization angle, then you shift the mean reflection point out of the center, of the geometrical center of this plate, and you get measurements up to 7-8 millimeters possible, and that's a huge amount for our millimeter goal. But there is no active use of such polarization effects.
I could imagine rotating the plane at some rate and then trying to use that as a look at what the response is from the different planes as it goes around. But
we have made such measurements, but instead of rotating, we can also rotate it. But instead of that, we used circular polarization and try to check out what will change if you have linear polarization or circular polarization.
Georg, when people are developing satellites to go into orbit, do you coordinate with them if you can to try to get something that will enhance your work so that you have can get better information?
Yes. All these laser stations are coordinated within an organization called ILRS, International Laser Ranging Service. So if you want to develop or build a satellite and put some retros on it, and you want us to track it, to range, then there is an official way you can address the organization and tell us about your intentions, and you will get, I don't know, a 10-page form you have to fill in, and which is intended as an assistance for you, because people are designing things which makes it almost impossible to do laser ranging to them. For example, they designed a satellite, put some retros on it, and launched it, and then said, okay, we have here a satellite, can you please range it? However, the satellite was launched into an orbit with almost zero inclination, on a very low orbit, and there is no station worldwide which could range to that, because it was just over the equator.
Is there financial incentive between your organization and manufacturers to assist them in putting this extra equipment on the satellite?
No, it is. Our organization is not based on anything financial. That means every station has to try to finance itself via some experiments, via some research money, whatever. Also, we are not asking for money, and we are, if we track the satellites, but this is a decision of our ILRS organization. And our main objectives are, it has to be something for science only. Mainly we try to avoid commercial, and we definitely do not track any military stuff.
What is there a parent body? Like, do you report to the UN, or is it just a bunch of academics that got together and they formed this organization and they coordinate? You know, what's the political side of it?
This was suggested by some body, and it's not anything by UN or by any other institution. It's a self-administrative organization just to coordinate this activity, based on the on that. If you have a laser arranging stations and you do some measurements, it's good for nothing or almost nothing. It only makes sense if you make this worldwide. For example, if we have a problem, even with space debris, that's the same. If we have a problem with space debris and said, okay, yes, but we have, for the next 2 days, we have clouds, cannot do anything because we need a clear sky to do our measurements. But we can inform Chinese stations. They also have space debris capability, and try to ask them to help. So this is also on a just an internal level. No large organization behind that. Just self-administration.
Now, do these same stations, are they the ones that Mike Perlman can use for his geodesy work? Do you guys share that?
Yes, exactly. All these stations which are participating in this ILRS, they do their measurements. They deliver the data into some data centers. We have groups of people who deal with the data, who check the quality, who check that there are no wrong measurements inside. They define formats and so on. On the other hand, we get out of that if we get much better predictions, because some people are using all the measurements worldwide and predicting the orbit for the next days, and we all can make profit out of that. That's exactly what Mike Perlman is our his official part. He's the general secretary of this organization, and he is doing that very well, and tries to keep that in some coordinated way.
Good. I see it's 11:30. We've taken a lot of your time, Georg, and thank you. Are there any other questions? Anything else that we want to ask Georg while we have him? Thank you again. It was so informative. I think we all learned a lot. Maybe more than we ever cared to know, but we learned a lot. And
I just hope I gave you enough stuff to think about, to check what's going up some 1,000 kilometers above your head.
You're currently in Austria, which means it's about 5:30 p.m.
Right. Yes.
Okay. That means it's dinner time. What are you going to have for dinner?
No idea. The kitchen is 1 story below Wiener Schnitzel. Yes, good idea.